this video, we are going to talk about the inverting input configuration of the operational amplifier, and we will see the concept of virtual ground in the op-amp. Now in the last video, we had seen the basics of this operational amplifier, and we had seen that this op-amp is a very high gain differential amplifier, and the gain of the op-amp used to be in the range of 10 to the power 5 to the 10 to the power 6. And we had seen that even if we apply a very small amount of differential input voltage between the input terminals of this op-amp, then also the output will be get saturated towards the bias points. And then we had seen the voltage transfer curve of this op-amp. And then we had seen that even if we apply a small input voltage to this op-amp, then also the output will be get saturated either towards the positive or the negative saturation voltages. Now let's say the saturation voltage for the op-amp is 10 volt and the open loop gain of this op-amp is, let's say, 10 to the power 6. So this op-amp will be get saturated at a 10 microvolt of differential input voltages. So now whenever we want to use this op-amp as an amplifier, we need to use this in a linear region, that means in this region, so that the input and output has a linear relationship. But whenever we are using this op-amp in open loop configuration, then this linear range is very small. So if we want to use this op-amp as an amplifier, then we need to somehow control the gain of this amplifier. And we can do so by applying the feedback from output to the input side. So there are two ways by which we can apply this feedback. One is providing the feedback from output to this positive input terminal, or let's say non-inverting input terminal. And the second is providing the feedback from output to this inverting input terminal. Now whenever we are providing the feedback from this output to this non-inverting input, then that kind of feedback is known as the positive feedback, because here fraction of the output voltage is getting added to this non-inverting input. Now whenever in any system we are using the positive feedback, then this positive feedback leads that system into the instability. So we cannot use this positive feedback alone. So now here, to control the gain of this op-amp, we need to go for this negative feedback. That means we need to feed the fraction of output voltage to this inverting input terminal. Now here there are three ways by which we can apply the input to this op-amp. The first is applying the input to this non-inverting input terminal and grounding this negative input terminal. Second is providing the input to this inverting input terminal and grounding this positive terminal. And third is providing the input to both the non-inverting as well as the inverting input terminals. So first we will see the case when we are applying the input to this inverting input terminal. So let us say we have applied the input to this inverting input terminal through one resistor R1, and we are providing the negative feedback from output to this inverting input terminal via this feedback resistor RF. So now whenever op-amp is used in this configuration, then this configuration is known as the inverting op-amp configuration. So now in this configuration, let us find out the relation between this output and the input voltages, and let us see how we can control the gain of the op-amp by using this feedback resistor RF and this resistor R1. So let us find the relationship between this output and input in terms of this feedback resistor RF and R1. So now before we derive this expression, let us understand the concept of virtual ground in the op-amp. And this concept of virtual ground is applicable when we are providing the negative feedback to this op-amp. Now let us say for the given op-amp, the open loop gain of this op-amp is 10 to the power 6. And we know that the output voltage Vout of op-amp can be given as A times the differential input voltage. That is the input voltage between this inverting and the non-inverting input terminals. Now here let us assume that through this negative feedback, we are controlling the output voltage of this op-amp in such a way that the output voltage is always less than the saturation voltage. Or we can say that we are operating this op-amp in a linear region. So let's assume that the output voltage is 10 volt. So we can say that 10 volt, that is equal to 10 to the power 6 times this differential input voltage, or differential input voltage is equal to 10 microvolt. Now here this differential input voltage is nothing but the difference between this inverting and the non-inverting input terminals. So we can write this differential input voltage as V plus minus V minus, that is equal to 10 microvolt. Now here this 10 microvolt is a very small signal and we can almost neglect it. So we can write this V plus minus V minus as approximately equal to 0 volt. Or we can say that V plus, that is equal to V minus. It means that the inverting and the non-inverting input terminals are at the same potential, or we can say that there is a virtual short between this inverting and the non-inverting input terminals. Now here the term virtual means that these two terminals are not actually short circuited, but they are virtually short circuited. So whatever voltage that appears at one terminal, the exact same voltage will be appear at the another terminal. So now in this configuration, this non-inverting input terminal is grounded. So we can say that V plus that is equal to 0. So according to this conclusion, V minus should be equal to 0. It means that this terminal is not actually grounded, but it will act as a virtual ground. So this negative feedback will ensure that the difference between this inverting and the not inverting input terminal is very small, or we can say that it is almost negligible. And because of that, we can consider this both input terminal at a same potentials. So this concept is known as the virtual ground concept. So now let us use this concept of virtual ground and let us derive the expression between this V out and V in. Now here let us say the current I1 is the current that is flowing through this resistor R1, and let us say this node is the node X. And let us say the current that is flowing through this resistor RF is IF. Now in the last video we had seen that the op-amp has a very high input impedance, or if we consider the ideal op-amp, then the input impedance of the op-amp is infinite. It means that no current is entering into this op-amp, or we can say that current I that is equal to 0. It means that I1 is equal to IF. So now we can write this I1 as V in minus Vx divided by R1, where Vx is the voltage at this particular node. Likewise, we can write this current IF as Vx minus Vout divided by RF. Now, if we apply the concept of virtual ground, then this node X should have a zero potential because this non-inverting input terminal is grounded. So the value of Vx should be equal to 0. So we can write this expression as V in divided by R1 that is equal to minus Vout divided by RF. And if we rearrange it, then we can write it as a Vout by V in that is equal to minus RF divided by R1. And this expression is known as the closed loop gain for this inverting op-amp configuration. So as you can see here, just by changing the value of this RF and R1, we can control the gain of this op-amp. And we can use this op-amp as a amplifier. Now here the negative sign indicates that the output voltage is 180 degree out of phase with respect to input voltage. So let's say if we have applied the sinusoidal signal at the input, then at the output we will get the amplified sinusoidal signal which is having a 180 degree phase with respect to input signal. And that is why this configuration of the op-amp is known as the inverting configuration, because the output will be get inverted with respect to input voltage. So let's say in this case, if RF is equal to 2 kilo ohm and R1 is equal to 1 kilo ohm, then the gain of the op-amp will be equal to 2. And suppose if we apply the 1 volt of signal, then at the output we will get a 2 volt of signal which is 180 degree out of phase with respect to 1 volt signal. So in this way, by controlling the value of RF and R1, we can control the gain of this op-amp and we can use this op-amp as a amplifier. So I hope in this video you understood the inverting op-amp configuration and the concept of virtual ground.